Hello everyone, JP here and welcome back to Chemistry 3120. First 9 lectures we covered quite a bit with respect to chemoselectivity. We're going to switch gears a little bit today and we're going to talk about the alkylation of enolates. So that will be the focus for the next probably 2 to 3 lectures. And as I mentioned, a lot of this stuff is found in chapter 25 of your textbook. Okay, so let's take a look at what enolates are, how we generate them, and how we can control their appearance, or how we can control how to generate them. So here are a few examples. Okay, so I've drawn 5 molecules here, and the question I want to ask to you is, where can we, or how can we generate enolates? Is it possible to generate enolates? So recall that enolates are formed when you have a compound like this, and then you have an alpha carbon, and thus you have an alpha proton. So under basic conditions, you can remove this proton and you can delocalize electron density into that carbonyl system, as I'm showing you here. So let's take a look at this compound here. Can we form an enolate from this compound? So the first thing to do is look for alpha protons. So you have 2 different alpha carbons. You have an alpha carbon here, another alpha carbon here. It's asymmetrical, so you have 2 different types of alpha protons. So let's take a look at, let's call these HA, and therefore if you had a base, your base could remove one of these protons and you could generate an enolate that looks like this. So that's one potential enolate. The other potential enolate is if you take these protons here and then another base, or maybe even the same base comes, removes that protons, pushes electrons up into that carbonyl, and there's your other enolate. So for this structure, you have 2 potential enolates. Let's move on to this structure here. How many different enolates can we make? So look for your alpha carbon and then see which protons are acidic. This is ipso. This is the alpha carbon. Do we have any alpha protons? No, we don't, because this carbon here is fully substituted. So we can't do any type of elimination to form an enolate. And do not try to remove this proton here. This proton is not acidic and it's directly bonded to this carbonyl group here. So this is not an alpha proton. Okay, so this compound is not enolizable. Okay, what about this compound here? Here we have a ketone, and again, look for alpha carbons. Here's an alpha carbon, here's another alpha carbon. Here, this is fully substituted, so you can't take protons from anything because there are no protons. And here you do have a proton. So in terms of generating an enolate, you have one potential enolate to make. There it is right there. This compound here, let's take a look at, it's a lactone, and you definitely have an alpha carbon, and you have a beta carbon, gamma, so on and so forth. Now the question is this proton acidic? If you try to take a base and put the protons here, you know that's just not going to work. You already have a double bond here, and even if you delocalize into here, the geometry is just not going to add up. So because of conjugation, and because this is sp2 hybridized, this is not acidic. However, if we look at not the beta protons, but the gamma protons, if you try to remove these, what you'll see is that because you have a conjugated system here, you can actually move the electrons up into this scaffold. So if you do that, you will generate this structure here, which is also an enolate. And then finally, this compound here is benzaldehyde. Do we have alpha hydrogens on here? No, we don't. This is not enolizable. So enolates are formed under carbonyl compounds under basic conditions, provided that one, there are alpha protons or conjugated gamma protons. And number two, that the anion that you make can be stabilized through resonance. So I'll put number two here. So along this point of number two, I will show you how some people denote these enolates. So maybe I'll just take a look at this first example up here. What some people will do, and this is absolutely fine, is they will put the negative charge on that negative carbanion like this. And that's correct. That's fine. The reason that these are formed and are stable is because you have this anion here that can move through resonance and form this enolate structure. My preference when I draw enolates is to have and to show the contributing form with the oxygen holding that negative charge. And I do that because I know that oxygen is more electronegative than carbon, and this is probably going to be the more stable resonance structure. So in all the enolates, or most of them that I will be drawing, I'll immediately go to the enolate structure. However, just letting you know that these two are in fact resonance structures and they are both equivalent. All right, so let's talk a little bit about carbonyl groups, since we'll be focusing on them and how they can show quite a bit of diversity. So you've learned already that carbonyl groups are excellent groups to be attacked by a nucleophile. And we looked at some examples in chapter 23, looking at reduction of these compounds, protection of aldehydes, so on and so forth. So carbonyl groups, to no surprise, are very reactive to nucleophiles. So this offers organic chemists a good pathway to generate different types of compounds. In addition, as you've just learned here, carbonyl groups also have the potential to enolize if they have an alpha proton. So carbonyl groups are quite interesting because they show what we call diversity, meaning that they can be attacked as an electrophile, as shown here, or they can actually form enolates, which we'll learn soon are actually nucleophilic. So one of the questions that we are going to have is how can we control the type of enolate that we make? How can we ensure that we only get an enolate forming and not reaction of a nucleophile to a carbonyl compound? So that's going to be a large focus of this unit and chapter. Some other things about carbonyl groups and enolate formation is what kind of base are we going to use when we do these types of reactions? So we have two main types of bases when we're talking about enolates. And let's think back to pKa of alpha hydrogens that are adjacent to carbonyl. If you think back to our first lecture, those types of compounds have pKs of around 19, 20 to 21. It really depends what's attached to that R group. But let's just say around 21, low 20s for the time being. So one way we could generate an enolate is if we take a very strong base whose conjugate acid has a much higher pKa. So let's say we got B, and let's call this a strong base. If this base comes and removes that proton, you generate your enolate plus your conjugate acid. And let's assume that this is a very strong base, so the conjugate acid of that reaction is going to be quite high. So in this case, let's say the pKa of this is going to be much greater than 21. Okay, so that's just one example. One example of a really good strong base that we have looked at is something like sodium hydride. So sodium hydride, its conjugate acid is H2, and H2 is quite stable, and it has a pKa of around 36. So you know, based on our acid-base principles, that this is essentially going to be irreversible. So that's one way you can generate enolates. What about using a weak base? And we typically sometimes call these reversible bases. So what if we take the same structure and use a weak base and let's say we generate our enolate, and you'll generate the conjugate acid, and the pKa for this will be much less than 21. One example of this might be something like triethylamine. The conjugate acid of triethylamine is around 9 to 10. All right, so if you're using triethylamine as a potential base, it's a weak base, it's going to generate this, but you know that based on acid-base principles, if this is 21, and triethylamines conjugate acid is around 10, the equilibrium is going to fall heavily to the starting materials. So you're just going to have a little tiny arrow going this way. However, we are going to be using both types of bases for alkylation, and you might be wondering how that happens. So before I do that, no one corrected me here. I have, I don't know why I put an oxygen there, so make sure you erase that. That's a double bond. Because what we're going to be doing is we're going to be combining both of these reactions with electrophiles. So we'll call that E+. And once we get our electrophile in place, you'll get alkylation of enolates, which is the focus of this chapter. And there's your new compound. But can we do this with a weak base? Can we take an electrophile, and if we're only generating a little bit of this, how is it that we can make this reaction work? Well, think of Le Chatelier's principle. Even if you have just a small percentage of this in solution, as soon as you have this react with the electrophile, then that shifts everything over just a little bit. So the real driving force is the electrophile and pushing this irreversible reaction down here. But it's important to understand the acid-base properties of every reaction beforehand so we understand how to generate different types of enolates when the time comes. Okay, so there is your structure. We can look at not only enolates like I've shown here, but I call them enolate lookalikes. So what are enolate lookalikes? Well, they look like enolates, but they're not really. So basically what you've seen is that enolate can form because the anion, the carbanion, can be stabilized through this electron withdrawing group. So are there other groups there that can be used in a similar fashion? Well, I wouldn't be bringing this up if there weren't. So here is a nitrile group. So if we take a base, and here's an alpha proton, I'll put that electron density onto that carbon. And you can see here that you can actually resonance stabilize this nitrile compound and put the electron density onto the nitrogen. So this would be a suitable resonance form. In addition, you could take a look at a nitrile compound and you could do the same thing. You could take a base, form that carbanion. I'll draw the actual structure of the nitrile group so you can see where the charge distribution is. And then you can see now how if you put the electrons from that carbanion, you can actually stabilize it into that nitrile ring. Okay, so there's another resonance form. And then, like enolates, these would react with electrophiles in that you could get reaction occurring through this nucleophilic carbon, and this will be a great way to add substituents to your desired compound. So that works nicely with enolates, with nitrile compounds, with nitro compounds. Okay, so let's take a look at a couple examples. Nothing too crazy here. Everything, I hope, is pretty straightforward so far. right, so let's take a look at so we have this nitrile compound, we have this alkyl halide, we have sodium hydroxide, and then we have this triethylamine, like butyl chloride reagent. And this is actually like a phase transfer catalyst. It helps to solubilize a sodium hydroxide within this organic solution. So don't get distracted by that, but let's focus on what the final product would look like based on our understanding of enolates, how they can form, and alkylation. So where can we form an enolate? So you can form an enolate look-alike right at this carbon. You know it's stabilized through the nitro group, exactly like how we did there. This will be your nucleophilic carbon, and then this will react with the alkyl halide and do SN2 chemistry, displace off that bromine. Okay, so your final reaction will look like, or your product will look like this. Okay, so pretty straightforward. Let's look at another example. Here we're going to use sodium hydride. We're going to use actually 2 equivalents. And then we're going to use excess methyl iodide. Okay, what is the product? So I'll let you think about that while I grab my coffee. Sodium hydride is a strong, essentially irreversible base. So you know it's going to remove one of these alpha protons, but we have 2 equivalents. So why don't we first look at the case in which we do a first deprotonation with H-, right? We're going to put that electron density here. And I'm just highlighting the mechanism so we can understand better what's happening. So there's your carbanion, but it says we have 2 equivalents of sodium hydride. Now, do you see other sites within this molecule where we can deprotonate? We still have an alpha proton here, but there's a negative carbanion here. So there's no way you can put 2 negatives on a carbon. All of these other hydrogens here are sp2 stabilized, so they're not acidic whatsoever. So what's the purpose of the 2 equivalents? Well, let's not worry about that for now. Let's look at what we're adding. We're adding methyl iodide, so 1 equivalent, or actually excess, but we can add 1 equivalent at a time. So here's a methyl iodide, it's simple SN2 chemistry. So when that happens, we have 1 methyl group attached to that carbon. Here's your cyano group. You still now have an alpha hydrogen, alpha proton. Now this is acidic because we've done that alkylation. So now your second equivalent can come in, form that carbanion, stabilize it through the nitro group, then it comes back and then reacts with another molecule, methyl iodide. So your final product will look like will look something like, well, will look exactly like that. And let's just do one more quick example. Okay, we take these two molecules together. We're going to use this tetrabutyl hydroxide, which is, again, a phase transfer reagent. You have these butyl groups, but you have now this hydroxyl group, which can act as a suitable base for this reaction. And you can do this in water and benzene, which are normally, well, which don't mix together, but with the phase transfer catalyst, you can get a homogeneous solution. So what is the product going to be? So you have a nitro group here, but do you have any alpha hydrogens to stabilize that? No, you don't, right? Here you have a nitro group. You can stabilize this carbanion, right? If you take this alpha hydrogen and stabilize it. So you can imagine that this is going to be your nucleophile, and that's going to react at that carbon here and displace off the chlorine group. Okay, so what this will look like is it will look something like that. That's your product. So I think you get the hang of it in terms of how to generate these compounds. All right, so let's take a look at the choice of electrophile for alkylation. With the examples I've shown, they've been relatively straightforward electrophiles, and they've been very good electrophiles. However, what we'll learn and what you'll see is that not all electrophiles are created the same. Some are better than others, and it's important for us to understand, decide which electrophiles to use for which type of enolates. So this is called choice of electrophile for alkylation. All right, so let's take a look at some very reactive species. So one of them we looked at was methyl iodide. So methyl iodide is very electrophilic. There's barely any steric hindrance. So methyl iodide, methyl chloride, methyl bromide, those would work really, really well. Other good compounds are these types of compounds, which are benzyl halides. These are sort of special compounds because this electrophilic carbon here, due to the benzylic nature of it, is really, really reactive. So these work really quite nicely as electrophiles. And then finally, other good electrophiles include these types of compounds in which you have an allyl group and then a carbon next to an X group. So something like allyl halides are just very good reactive substrates. So I would characterize these as being excellent electrophiles. Now, if we move over a little bit and look at the next class of electrophiles, we use one up there, which is primary alkyl halide. Okay, so I'll just call this an alkyl halide like this. So a primary and these ones are pretty good. They are reactive, but they're not as reactive as these ones, but they're still, they're still quite decent. So let's call these very good electrophiles. So here, primary alkyl halides. The next one's going to be secondary alkyl halides. So this is where if you have something like an alkyl halide that might look like this, and now you can see you're starting to generate some steric bulk there. And these ones actually alkylate pretty slowly and pretty poorly. So they're certainly not our first choice if we want a robust alkylation reaction. And then finally we would have tertiary alkyl halides. And as you might imagine, these ones here actually don't alkylate at all whatsoever. You have essentially a tertiary center where you cannot do SN2 chemistry on. So imagine you have an enolate here. It's impossible to do SN2 chemistry on there. You cannot do you can't do SN2 chemistry. And in fact, the other risk that happens, and I'll just erase this R prime group and you'll see why. I'll just move it up here. I'll put a proton up here, actually a couple of them. What can actually happen is that your enolate will come down. The double bond, because it can't reach the site, will more likely pick up this proton, and then you eliminate a double bonded compound and then release off the X group. So, in fact, elimination is likely, and that does not get you your compound. Okay, so I'll just write here, no alkylation. Now, later on in this unit, we're going to learn strategies to make this reaction occur, and we can't disobey the rules of organic chemistry. We can't make something go via SN2 when it's impossible. So what we're going to learn is we're going to learn to strip off this halide group via SN1 and then have some type of reagent come in and react. So those are some tricks that we'll learn later. But these are the general trends as we go from left to right. And in general, as you go from left to right, the risk of elimination, as I'm showing you here, increases as you go from here all the way up to the tertiary one. So with the tertiary alkyl halides, it's definitely perhaps one of the only side products that you'll get. But that risk is inevitable also with secondary alkyl halides and also primary alkyl halides. You can imagine that you have a proton here, you could form that double bond and kick off the halide group. So as you go from left to right, you increase the risk of elimination as the degree of substitution increases. And no reaction would occur. Okay, let's talk about an enolate that is asymmetrical, and let's talk about how we can control how to make one of the enolates or the other one. So, well, best thing to do is just draw the structures and talk about it. So very similar to one of the first examples we looked at when we were trying to first understand how to make enolates. We had this cyclohexanone, and then we understood we could deprotonate from one side or the other side to give two different types of enolates. So here with this compound, you can see that you have two different types of protons. Okay, we can just call these HA if we'd like. And then here we have these ones HB. And their relative pKa are going to be about the same. So they're going to be about 21. Yes, there will be subtle changes in them because of the R group, and they're not going to be exactly equivalent, but they're going to be pretty much the same. They're going to be essentially equivalent for our purposes. So let's take a look at these two different structures and try to understand if we can make one versus the other. So let's take a look at these HA protons, and this is what our enolate will look like. That's one potential enolate. On the other hand, if we take these protons here, let's take a look at what that enolate will look like. It's going to look like this. So how can we generate one versus the other? And let's take a look at the energetic differences between these two enolates and how they're formed. So let's see, probably the best thing to do for me is to show energy and look at the energy of these structures relative to one another. Okay, so I'm going to put our starting material here. It's going to have this energy, this amount of energy. And I'm going to show the structure of, or the energetics of this enolate here. And I'm going to put it not too far off, but something like this. A little bit lower, perhaps. And then I'm going to show the energetics of that enolate. And this enolate is going to be, it's going to have higher energy around here. Okay, so we have the energy of these different structures. Now, imagine you are a base. Okay, so you're a base and you want to retrieve a proton because that's your life mission, to pick up a proton. If you were to pick up one of these protons, which proton do you think would be easier to pick up? I mentioned that the pKs are about the same, but you're going to go for the low-hanging fruit because it's just easier to get to, right? There's less steric hindrance here. So in terms of the energetic pathway to remove these protons, it's going to look something like this. Okay, so there's going to be some hump you have to do to take that base, or to take that proton and it's going to look something like this. In contrast, if you want to remove these protons here, it's going to require a little more energy because you have this R group that's in the way. So in terms of what this will look like from an energetic standpoint, I'll just move this arrow because what you might imagine is that it's going to require more energy, and it's going to look like this. All right, so we've generated two different enolates, and they have two different energetic pathways based on how to generate them. Interesting. This one here is less stable, but easier to make, whereas this one here is more stable, but requires more energy to make. So why is this one more stable compared to that enolate there? This one is more stable because it's a more substituted double bond. Recall Zaitsev's rule from second year organic chemistry. The more substituted double bonds are, the more stable those compounds are. So you can think of this double bond having 1, 2, 3 substituents attached, whereas this double bond here has 1, 2, only 2 substituents attached. So that's why this one's more stable. All right, so this one requires more energy to make, is more stable. We call this one the thermodynamic enolate. In contrast, the one on the right is easier to form, but is less stable. So it's faster to form. This one's called the kinetic enolate. All right, so thermodynamic versus kinetic control. How can we control which enolate we want to make? If we throw a base in, is it going to generate just a kinetic one or just a thermodynamic one or maybe a mixture, right? So we need to understand how to control that using principles of thermodynamics. Okay, so we've already talked about thermodynamic enolates. They are more stable and more substituted. And kinetic enolates are less substituted and less stable. So how can we generate these? Let's look at and think about some specific conditions. Let's talk about energy in the pathway. That's one of the more easier variables. With kinetic enolates, you typically don't need as much energy. In fact, you want to keep probably that energetic barrier quite low. So in terms of reaction temperatures, for kinetics, we'd want to keep that temperature typically cold. So low reaction temperatures. In contrast, for thermodynamic enolates, you want to give it enough energy, and the easiest ways to add heat to that system. High reaction temperatures, low reaction temperatures. Let's talk about bases. Now, I know we haven't talked too much about bases, but imagine we have something called a strong sterically hindered base that only likes protons that are easier to get to. For kinetic enolates, that's the type of base we want to use. We don't want a base that would actually have a high chance of reacting with those ones. So we want to use typically a strong, sterically hindered base. Whereas for this one here, we typically want to use like a weak reversible base. And that might seem counterintuitive, but when we have a weak reversible base, we increase that reversibility, and if we give it enough time and temperature, then we can increase the chance that it'll generate the more stable compound. Ultimately, this is the more stable compound, so if you give it enough time and energy, this is what it's going to want to make. So related to that, we talked about high reaction temperatures, so longer reaction times. Yeah, okay, so there was a bit of a, it was kind of funny. I ended this lecture just 3 minutes, but my camera stopped recording for some reason. So I'm just going to finish up what it missed. We were just talking about longer reaction times. And so for longer reaction times, we want to give it more chance, more energy in the system in order to generate a thermodynamic enolate. For short reaction times, we want to only give it the opportunity to make the kinetic enolate, so it can't reverse back. So the other thing that we can use to control this are things like aprotic solvents. So aprotic solvents are things like THF, which don't have protons that can be used to donate. So aprotic solvents would be useful because in your kinetic enolate, you don't want to have a proton available to reverse that reaction and go back to that starting ketone. Whereas with thermodynamic enolates, you want to give it enough chance to go back and forth so that ultimately the thermodynamic enolate can be made. So protic solvents are typically used, and these are things like methanol or ethanol. The other thing that I want to talk about is stoichiometry. So we haven't talked about stoichiometry, but if you're doing these reactions, you can imagine that we're thinking 1-to-1 ratio. 1 equivalent of base, 1 equivalent of ketone to generate 1 equivalent of the enolate. However, in kinetic enolate conditions, we typically want to use excess base, and that's because we want to have excess base to take these protons and not give it the opportunity to go back. Whereas with thermodynamic enolates, we want to typically add excess ketone so that we give it more chance to go back and forth to ultimately make this compound here. And then finally, in terms of conditions, we want to use counter ions with these bases. I'm going to talk about these different types of bases in the next term, not next term, the next lecture. And if we use something like a lithium counter ion, what this does is that it will take the enolate and form a pretty strong ionic bond between the oxygen here, meaning that this is not super reactive. However, if you look at bigger ions like sodium or potassium, these are much larger and these have a weaker ionic bond with the enolate, thus making them more reactive, more likely to reverse and ultimately go to the thermodynamic enolate. So typically for thermodynamic conditions, we typically want to use sodium and potassium counter ions and lithium for kinetic enolates. Okay, so that's it for today's lecture. We're going to tune in to lecture 11 soon, which will talk about sterically hindered bases and continue this discussion. All right, see you soon.